Hi, hello. Hope to find you well. My name is Victor Neto, and I'm gonna speak to you about graphene-based sensors for indoor air quality monitoring. I'm a professor of advanced manufacturing technologies at the Department of Mechanical Engineering of the University of Aveiro in Portugal, and a researcher at the Center for Mechanical Technology and Automation. TEMA is a research center founded in 1996 within the Department of Mechanical Engineering of the University of Aveiro and aims to contribute to sustainable manufacturing solutions and to technologies for the well-being. My presentation will start with a short introduction, some information about air quality requirements, parameters, assessment, the state of the art on sensors for air monitoring, and then an introduction to graphene-based sensors as potential air monitoring, followed by some highlights on graphene properties, synthesis of graphene, and the need to functionalize graphene for air monitoring. I'll end with some conclusions and future work. In modern society, exposure to multiple airborne pollutants is almost unavoidable, as we spend the majority of our time living, working, and traveling within closed indoor environments. The exposure to these ubiquitous contaminants, for example, bioeffluents, particulate matter, formaldehyde, and other volatile or semi-volatile organic compounds, molds, radioactive gases, etc., could adversely affect occupants' health, comfort, and productivity. Indoor air pollutants might be originated from a range of sources, namely from building materials, heating systems, furniture, and decoration materials used, materials deterioration, paints, varnish, and preservatives, insoluble nanoparticles, as well as biological particles. Most gaseous pollutants are inhaled and affect the respiratory system, but can also affect the cardiovascular, nervous, the digestive, and urinary system, induce hematological problems, nausea, and cancer. The size of the particles determines the site in the respiratory tract that they will deposit. Particles between 2.5 and 10 microns are deposited essentially in the main bronchi. There is strong evidence to support that ultrafine and fine particles are more hazardous than coarse particles in terms of mortality and cardiovascular and respiratory effects. Sensors are physical, chemical, or biological based devices that can translate the polluant's concentration into a signal, most of the cases into an electrical signal. One can make a classification of different sensors according to their operating principle. Therefore, one can have sensors based on electroconductivity variation, such as metal oxide semiconductor sensors, and other kinds of variation, such as optical sensors using fluorescent or absorption of light. Metal oxides have been used for monitoring volatile organic compounds for more than 50 years due to their semiconducting properties. Semiconducting metal oxides such as tin dioxide, zinc oxide, titanium dioxide, nickel oxide have been attractive for gas sensing applications since they are cheap, flexible to apply to different manufacturing methods, and easy to use. The main advantage of titanium dioxide gas sensors compared to other metal oxides is that titanium dioxide has much lower cross sensitivity to humidity. As referred, metal oxide semiconductor sensors based on conductivity variation have been used to monitor pollutants for a long time due to their semiconducting properties. Besides the already mentioned titanium dioxide that has been used extensively for gas sensing applications, tin dioxide is undoubtedly the most studied material and it has been applied to many commercial devices on the market. Zinc oxide is another N-type metal oxide semiconductor that is used on gas sensing not only for its chemical and physical properties but also for its non-toxicity and low cost. Among P-type semiconductors, nickel oxide is an attractive material not only for its gas sensing properties but also for its application due to its catalysis and electrochromic properties. Indoor air quality monitoring is based on two basic criteria: comfort, and health. This is a rather complex and comprehensive concept, which depends on a large number of factors such as temperature, relative humidity, airborne particles, polluting gases, among others. Temperature and humidity are relative simply to measure, but as referred earlier, there are a great number of airborne particles and gases that might be found indoor. Ambient air quality standards require the monitoring of volatile organic compounds, breathable particles with an aerodynamic diameter smaller than 10 micron, and with an aerodynamic diameter smaller than 2.5 microns, carbon dioxide, carbon monoxide, nitrogen dioxide, ozone, sulfur dioxide, ammonia, benzene, hydrogen sulfide, and formaldehyde. For air quality measurement, numerous indices have been proposed. The first index was the Pollutant Standard Index, which was modified and replaced by the Air Quality Index, both of which were developed and introduced by the United States Environmental Protection Agency. The Daily Pollutant Standard Index is determined by the highest value of one of the five main pollutants: sulfur dioxide, ozone, nitrogen dioxide, carbon monoxide, and particles smaller than 10 micrometers. The slide table presents values established by the International Standard Organization, World Health Organization, and the American Society for Heating, Refrigerating, and Air Conditioning Engineers for some parameters that define the indoor air quality. The substances considered are present in indoor sources, and when their limits are exceeded, it represents a risk to health. Conventional analytical instruments such as mass spectrometer, nuclear magnetic resonance spectroscopy, and chromatography can be used accurately to measure the concentration of pollutants inside the buildings, but it is not practical because they are bulky and complex instruments. In addition, most analyses require sample preparation, so real-time analysis is difficult to obtain. Solid-state chemical sensors have been widely used. However, also their measurement accuracy is limited and present a long-term stability problem. Nanotechnology comes to fill existing flaws by providing numerous opportunities for the development of the next generation gas detectors, with enhanced sensor performance such as high-specific, fast response, ultra-high sensitivity at extremely low concentration, as shown in the slide table, fast recovery, low power consumption, room temperature operating, and good reversibility. In the recent years, there has been a significant improvement in the construction of sensors with the incorporation of several nanomaterials, such as nanowires synthesized from metals, for example, nickel, copper, gold, platinum, metal oxides like zinc oxide, tin dioxide, iron oxide, semiconductors like silicon, indium phosphide, gallium nitride, carbon nanotubes, and metal nanoparticles based on gold, copper, palladium, cobalt, silver, or platinum. Nanostructures have a high surface-to-volume ratio, which is one of the most important characteristics of a material to be used for gas sensing, and provides large active surface area for the interaction of gas molecules. This strongly favors the absorption of gases on nanostructures and leads to highly sensitive sensors performance. In addition to the high surface volume ratio, one-dimensional nanostructures are particularly suitable for gas detection applications based on their good thermal and chemical stability and sensitivity of electrical properties to change in the surroundings. These one-dimensional sensors have demonstrated high sensitivity down to part per billion levels, fast response, good selectivity, low power consumption, and miniaturization. Graphene has proved to be an excellent nanomaterial for application in gas vapor sensors, due to their variety of structure, unique sensing performance, room temperature working conditions, and tremendous applications prospects. Compared to other materials, graphene showed great potential for the construction of sensors, due to the combination of extraordinary properties such as atomic thickness of graphene sheets, high carrier density, extreme high surface volume ratio, and unique electrical properties such as high mobility and low electrical noise. makes such material highly sensitive towards the change of local environmental conditions, which is an important advantage in the sensing field, since all carbon atoms interact directly with the analysis, thus promoting higher sensitivity. One of the key limitations of sensitivity is fluctuations due to thermal motion of charges and effects. Graphene sensors are capable of detecting individual events when a gas molecule attaches to graphene surface. The absorbed molecules change the concentration in graphene one by one electron, which leads to changes in resistance. The achieved sensitivity to the fact that graphene is a low noise material electronically, which makes it a promising candidate for gas sensors for hydrogen, water, carbon monoxide, ammonia, nitrogen dioxide, dichlorine, ethanol, iodine, and oxygen. The combination graphene zinc oxide hybrid and reduced graphene oxide was already used to develop high efficiency gas sensors. Palladium decorated graphene was able to detect hydrogen in the concentration range of 25 to 10,000 ppm. This sensor showed high sensitivity, fast response, recovery, allowing the use with multiple cycles. A set of sensors based on PMMA reduced graphene oxides and PMMA reduced graphene oxides nanocomposite was developed to be used as ammonia gas sensor. Greater sensitivity and selectivity was observed in the case of the PMMA reduced graphene oxide nanocomposite compared to the individual layers of reduced graphene oxide or PMMA. An acetylene gas sensor was obtained by synthesis of zinc oxide reduced graphene oxide hybrids loaded with silver, obtaining a low detection rate of 1 parts per million, rapid response of 25 seconds, recovery of 80 seconds, and good repeatability. Graphene's success has stimulated great interest and research in the synthesis and characterization of graphene-like two-dimensional materials, single and few atom-thick layers of van der Waals materials, which show fascinating and technologically useful properties. Graphene oxide, boron nitride, graphite carbon nitride, transition metals diclassorianide, transition metal oxide, and graphene are being also considered. Carbon is an abundant element playing a major role in the chemistry of life, taking the forms of fluorines, carbon nanotubes, graphene, graphite, and diamond. Graphene attracted extremely interest due to its exceptional characteristics. It is an extremely diverse material that allows producing different materials with variety properties leading to great technology advances. However, the absence of a band gap in pristine graphene constitutes an obstacle to be overcome in order to shape the transport properties by introducing a private energy band. The transport and optical properties of semiconductors and isolators are determined largely by the electronic band gap. The band gap is the energy required to promote a balanced electron bond to an atom to become a conduction electron, which is free to move within the crystal lattice and serve as a charger carrier to conduct electric current. If the valence band is completely full and the conduction band is completely empty, then electrons cannot move in the solid. However, if some electrons transfer from the valence to the conduction band, then current can flow. Therefore, the band gap is a major factor determining the electrical conductivity of a solid. Nevertheless, in the past decade, graphene has been the undisputed champion of the material world, thanks to its integration with different nanomaterials such as metals, metal oxides, and quantum dots, as referred earlier. The process of synthesis of graphene defines any technique used for fabricating or extracting graphene. This depends on the purity, crystallinity, and desired size of the product. Previous studies have shown that various techniques have been found for producing thin graphitic films. Synthesis methodologies of graphene can be divided in two main categories: physical and chemical methods, as shown in the slide table. Mechanical exfoliation can produce defect-free materials with exceptional properties. However, this method is not suitable for large-scale production. Graphene synthesis from reduced graphene oxides usually causes incomplete reduction of graphene oxide that results in the successive debasement of electrical properties depending on its degree of reduction. Of all methods used for synthesis of graphene, chemical vapor deposition is the most promising, cheap, and accessible. The CVD process is the most common method to grow graphene, which has been extensively investigated. It consists of breaking the bonds of the molecules of a gas subjected to high temperatures, so that the atoms coming from the gas are deposited on a certain substrate, and the graphene film synthesized by this method can be transferred to other substrates, facilitating their integration to various materials. The deposition of high-quality graphene from CVD process is usually done onto various transition metal substrates, such as copper or nickel. Copper is the most popular metal to produce homogeneous single-layer graphene in large area. However, the use of graphene for many applications is limited due to the copper contamination. The copper etching and graphene transfer process always leaves copper remains on the bottom side of graphene previously attached to the copper foils. In addition, at a typical graphene growth temperature of 900 to 1000 degrees C, copper gets partially melted and sublimated. The generated copper vapor easily contaminates the CVD chamber as well as the grown graphene from the top. CVD process can be of various types: thermal, plasma enhanced, cold wall, hot wall, reactive, and so on. This depends on the characteristics such as the material quality, precursor, the width, and the structure required. Graphene is intrinsically inert and non-selective. Its great efficiency to conduct electricity and distinguished feature of ballistic transport of charges decide that this two-dimensional material is an ideal candidate to serve as a platform or a supporter in which we can realize many specific functions by doping or compositing with other materials. Different doping and reaction conditions can lead to different types of graphene-based semiconductors, P-type or N-type. For example, one doped graphene shows characteristics of the N-type semiconductors when it is exposed to a reducing ether, such as ammonia. It would get electrons from the gas molecules, leading to an increase of the electron concentration. This is, a decrease of graphene resistance occurs. Likewise, when it is exposed to an oxidation atmosphere, such as nitrogen dioxide, it will deliver electrons to the gas molecules, leading to an increase of the hole concentrations and therefore to an increase in the graphene resistance. Surface modification of graphene can be achieved by various forms. Chemical functionalization of graphene can be of covalent nature, as shown in the slide schematics, or non-covalent. The structural alteration of covalent functionalization can occur at the end of the sheet and or on the surface. Surface functionalization is associated with rehybridization of one or more sp2 carbon atoms of the carbon network into the sp3 configuration, accompanied by simultaneously loss of electronic conjugations. Non-covalent interactions primarily involve hydrophobic van der Waals and electrostatic forces, and require the physical absorption of suitable molecules on the graphene surface. Atomic layer deposition has been also used to deposit materials in nanostructured carbon materials, and it can be a way of modifying graphene. For instance, tin dioxide can be deposited by ALD to form a compact sensing layer over graphene oxide. Getting to the end, with the ever-growing environment concerns, the detection and monitoring of various gas species are of crucial importance. Indoor air pollutants might be originated from a range of sources. Most of these pollutants are inhaled and affect human health. Nanotechnology comes to fill existing flaws by providing numerous opportunities for the development of the next generation of gas detectors with enhanced sensors performance such as high-specific, fast response, ultra-high sensitivity at extremely low concentrations, fast recovery, low power consumption, room temperature operation, and a good reversibility. awarded with high surface area, chemical reactive sites, and tunable chemical and electronic properties, graphene derivatives such as graphene oxide and reduced graphene oxide have already demonstrated a superior gas sensing activity over pristine nanostructured metal oxide, carbon nanotubes, and conductive polymers. Despite the interest in the study of nanomaterials have escalated in the recent decades, the application is still in its infancy. The accumulation of non-conventional properties has attracted researchers' attention, which are now actively developing technological approaches to graphene-based transistors. Graphene has significant applications in electronics, presenting itself as a strong candidate for the replacement of silicon in future solid-state devices. However, proper modifications are required to make use of these properties for gas sensing, which, as discussed, may be attained by proper functionalization. Considering sensitivity and selectivity as performance indicators, new dopants, functional molecules, and manufacturing methods should be explored as future works. Also, additional research on functionalization of graphene is necessary to improve its electrical conductivity and dispersibility. Finally, it should be noted that the method for the mass production of graphene has not yet been identified, being also a future work to be considered. Finally, I would like to take the opportunity to thank the conference organization for the invitation to present this talk and also acknowledge my co-authors, Denise Machado, Gonzalo Otero, Manoj Singh, Paula Marques, Ricardo Silva, and Rui Silva, and their respective organizations, the Center for Mechanical Technology and Automation and the Aveiro Institute of Materials. Also acknowledge Portugal 2020 program that is financing this project. And thank you for your interest.